Okay, let's look at the count possibilities question now. Basically, the question says that given a tree, we have to find, well, basically the topological orders. Let's talk about topological orders first. Topological ordering means an ordering in which if an edge exists between u and v and u points to v, in any topological order, u should appear before v. For example, in this tree, 1 should always appear before 2 and 4. And because 2 and 3 should always appear before 2. And because of this condition, 1 should always appear before 2, 3 and 4. And 2 should always appear before 3. And 4 does not have any constraint. It cannot appear any. It can appear only after 1. But it does not have any constraint on what it should appear before. And yeah, that is the meaning of topological ordering. For example, let's take the node 1 here. One should occur only after 3 and 1 should occur after 5 and before 5 and 4. And yeah, this is that is the meaning of topological ordering. And as you can see, there are many possible topological orders. And what we need is every one of the topological order will have only n elements, right? Because basically there are only n vertices. What the question is asking is we have to count the number of distinct vertices occurring at each position of the topological orders. For example, these are three possible topological orders for this given tree. And in the first index, only one occurs. So we are having one here. In the second index, or in the zeroth, it is the zeroth index, and this is the first index. And in the first index, 2 and 4 appears. So we are basically the count is 2. And for the second index, 3, 4, and 2. So a total of 3 vertices can occur in the second index. And for the third index, a total of 2 vertices can occur. And basically 2. So that's what the question states. So how we can actually solve this? Well, the brute force would be to generate all possible topological orders. And then for each one of the index, we'll calculate the distinct vertices and then put their values and then return it. But it should not work because the time complexity should be less than or equal to n log n. Let's do an observation now. What is the minimum index in which 2 can occur? Well, it cannot occur in the zeroth index. Why? Because it comes after 1, right? So it definitely cannot occur in the zeroth index because 1 has to come before it. So the minimum index in which 2 can occur is 1, or first index. The first index. And what is the maximum index in which 2 can occur? Well, it cannot occur in the last index. Why it cannot occur? Because 2 should come before 3. So the maximum index in which 2 can occur is 1 after the last index, 1 before the last index. And thus the possible indexes in which 2 can occur is 1 and 2. So 1 to 2, 1 comma 2. Let's talk about 1 now. 1 can appear only after 3. So the minimum index in which 1 can appear is the first index. Well, what is the maximum index in which 1 can appear? It should appear before 5 and 4 both. So the maximum index in which 1 can appear is 2 before the last index. So the possible index in which 2 can occur is 1 comma 2. Let's look at another example, 5. For 5, it should appear before 3, it should appear after 3 and 1. So the minimum index in which 5 can occur is the second index. And the maximum index in which 5 can occur is the last index. Because it does not have any children. There is no constraint on what is the last index it can occur. So 5 has a possible indexes of 2, 3 and 4. Well, given all these possible indexes, for example, let's say for 1 it was For 1 it was 1 and 2, right? And for 5 it is 2 to 4. So 2, 3 and 4. We can occur 2, 3 and 4. Well, given these intervals, we have to find in how many such intervals that, for example, in okay, the second index. So let's say we want to calculate the value for the second index. Let's say we want to calculate the value for the second index. We just have to calculate in how many of these intervals does 2 occur. That's the only thing that we have to calculate. And this can, and for each of the index you can do this. And basically taking an index and seeing in which how many intervals that does that index occur will take up n square time. We can do this easily using line sweep algorithm in n log n time. And what is the line sweep algorithm? The line sweep algorithm, it is beyond the scope of this video to explain the line scope algorithm because it takes quite a bit of time to understand what actually happens in that. So I'll suggest, so you solve a question called, suggest you solve this question called restaurant customers. If you can't understand restaurant customers, you can feel free to Google and YouTube. And yeah, the line sweep algorithm is just a part of it. Let's solve the other part of the question. Other parts of the question. So yeah, and let's formalize what the findings so far. In minimum index that node can occupy is the number of ancestors of the node. And what are the ancestors? Well, the number of ancestors is basically the level of the node. For example, the number of ancestors for 1 is 0. And for the number of ancestors for 3, it is 2 because it occurs at the second level 0, 1, and 2. Second level. And basically, the number of ancestors is 2 and 1 and 2. So it can occur from the second index onwards. The maximum index in which a node can occupy is n minus number of children of the node. Why n minus number of children of the node? Because it should appear before all of its children. So n minus number of children of the node is the maximum index that it can occur. And the node can occupy any index from the minimum index to the maximum index. And yeah, so we have to calculate for each node, we have to calculate the level as well as the number of children. If we calculate that, the question is basically over. And initially we have to have a good node, right? And we can basically find the good node. The good node is a node which has an degree of 0. We can easily do that here from the given inputs itself. And anything which has a degree of 0 is basically the good node. That's what we are doing till now. We are getting the 3 input and then basically finding the good node. And after that, what we are doing in the DFS carousel? Basically, saying basically in the DFS carousel, L is the level and C is being passed as a reference. And yeah, after calling each one of the DFS carousel, we are increasing the level by 1 because it goes depthwise. It goes depthwise. And we are appending the level to it. And then after appending the level to it, children, number of children. How will I find the number of children? Well, initially the value of C would be say curve C. Or let's say old C rather than curve C because it just feels better. Old C. Let's say the value of C initially is old C, and after traversing all of the children's node, it becomes C. The number of children is C minus old C. Why? Because for each one of the children, we are incrementing the C value by 1. And it occurs in each one of the DFS carousel, in each one of the nodes of each of the children. So C value gets incremented. And by this, we can basically find the number of the children of the node. And I'll explain what the query array does. Basically, we are saying that L comma 1 from the level onwards, you can the vertex can occur from the level onwards, which is L, and minus 1, and we are appending number of children comma minus 1, n minus number of children comma minus 1. Why are we appending this? Because we are saying that after this the vertex cannot occur. That's what we basically mean by this state, this slide. After n minus number of children, the vertex cannot occur, and from L the vertex can occur. That's what the queries are, I mean. And basically by doing the line sweep algorithm, we can find the number of vertices that can occur at each of the indexes. Thank you.